Good evening. Let's wait for a few more minutes and let others join.
Yes, sir. Sir,
Okay, so I think we can start now. Hi, good evening. My name is Umair Hussain. I am a PhD scholar in the Department of Mechanical Engineering, IT Madras, and I welcome you all for the sixth doubt session for the course Basics of Finite Element Analysis Part 2, which is a continuation to the Basics of Finite Element Analysis Part 1 course. This course continues the basics foundation laid by its predecessor course, and where in the starting of this course we discussed the basic formulation of the FEM problems in 1D particularly, and then in this course we started with first of all error estimation. We studied different various sources of courses of errors in the FEM solution, and how to quantify those errors. And then next step was to next topic in this course was the numerical integration calculations. So we studied some different types of numerical integration rules like trapezoidal rule, Simpson's rule, and then there are two other famous numerical integration rules, such as the Gauss quadrature and the Newton Cotes rule. So with that, we started with the introduction of the 2D the FEM problems in two dimensions. We started with the basic formulation of 2D problems, and then we moved on to defining and understanding the basic steps involved in the 2D FEM. So last week we started with the 2D FEM, and where we studied how to discretize the domain, what kind of issues can come into discretization of the domain, and then we studied how to get the weak form of the 2D FEM problems, and how to discretize how to get the elemental level equations for the 2D FEM problems. And then we started with the common types of elements used to discretize the 2D problems and 2D domains, and where we started with the linear three-noded triangular element, and we even derived the approximation functions for that element. So this week we continue our discussion for that, and we And now we move on to the linear four noded quadrilateral element. So here particularly we want to derive the approximation functions. So we are looking for a specific case. So we consider a case of a rectangle here. So we have a rectangle here of length A and its height width is B. So since we have four nodes, so of course we'll be having four unknowns in this in the approximation function here. So just like we did in the case of triangular elements, we consider one equation in the form of the four unknown constants here, and another equation for the approximation using the the summation of the nodal values at the four nodes of the element times the corresponding interpolation function. So in order to find the interpolation function, what we do is we substitute the values of these equations on each node for each node. So what we need to find is the values of these constants C1, C2, C3, C4 in terms of u. So we get the following equation, and if we solve them, we get the following results for the four constants. Just like the in the case of the triangular element, there we had three constants. Now we have four constants. So we get the values in terms of the nodal displacement values. So we substitute these values back into equation one, and we want to rearrange the equation in the form of this form, which means u1 psi1 plus u2 psi2 plus u3 psi3 plus u4 psi4. So we have only four nodes here. So this is how since we want the values of these functions, so we arrange the equation in this form. So doing so, we get this, right? So this gives us so coefficient of u1 would be psi1, coefficient of u2 would be psi2, coefficient of u3 would be psi3, and coefficient of u4 would be psi4. So thus we get the approximation function for the four noded rectangular element. Okay, so this was the case specific for the rectangular element. Same logic can be applied for any type of quadrilateral. We can take any random shape having nodes x1, y1, x2, y2, x3, y3, x4, y4, and we just substitute the values in equation 1 and 2, and we'll get a set of four equations with the four unknowns c1, c2, c3, c4. And in that case, solving the equation would be rather not so simple as we just did here. So that there will have a 4 by 4 matrix for which we have to find an inverse, and that's a long task. But that can be done, right? So that's how we can get the approximation function for any random quadrilateral element. Okay, so now the if we know till now we what we did is to calculate the interpolation function. Next thing is to calculate the actual values of the stiffness matrix and the force factor using these approximation functions. So in practically when we are solving an FEM problem, we don't use the analytical approach to solve any integrals. We just use the numerical integration scheme directly to get with the answer. But here since we are doing manually here, so doing if we have simple enough functions, we can do them analytically, and uh, we will use certain rules that will help us do that very easily. So there here for now we don't need numerical integration, but practically we usually do. Okay, so we, if you remember, we derived uh, the weak form for a general 2D FEM problem, and we got the long complicated expression for the Swiftner matrix like this. So we have all different combinations of derivative terms here. So for simplicity, we since a1 a12 all these constants are constant, we can just simplify these, break down this long integral expression into smaller integral expressions. So in order to find these, we introduce some standard formula for integration. This is nothing to do with FEM. This is just generalized rules for integration. So, yeah. So I don't think we need to go into much detail about this. Okay, so so first we'll look for in the for the case of a linear triangular element. So if you remember from the last class, we derived some expression for the general linear triangular element with the uh, any random position of the nodes. So here, if these alpha I, beta I, gamma I are some constant that for which we know the formula, right? So we can get the derivative of this function with respect to x here and with respect to y here. Right? So we starting with our first integral term Sij11. We had we got this expression, and for which we had an identity, right? So we can get the this integral value very directly, straightforward. So likewise for other Sij 1 to 2 1 2 2 would be very straightforward. So this is very lengthy procedure. For in real problem, we'd not be having a, a lot of these terms, so we can just skip it for now. So for Sij00, we had a rather longer expression because we still have the x and y terms here. So we'll have integral of x square, y square, all these. So we'll have a long expression. What's interesting is the this force factor here. So force factor, if you know, it's integral of f of times psi I dx dy. So f, considering f to be a constant, it's just simply the our shape function psi, integral of the shape function, which if we'll do the this integration, we'll get the common value for all f, right? So we get a value of fa by 3. So that means whatever load is or this entire triangular element. So F refers to the body load. So consider these arrows acting perpendicular to the paper. So you have a this load distribution on the entire triangle, this F, and F times A is the total load acting on this area. And so Fa by 3 means this load is equally shared at each node, which kind of makes sense, right? So whatever the load is equally shared on on each of the three nodes. Okay, so next thing is to calculate the stiffness matrix and force factor for a four-noded rectangular element. So for rectangular element, we since we know we have calculated the approximation functions for a specific type of rectangle whose origin was at 0 0, but it may not be the case every time, so we need to transform this to some other. So we need to transform our given coordinate system to this coordinate system, but it's still only for rectangle. Okay. So suppose we have some given coordinate system x and y here. Okay. So we have some given coordinate system x and y. So so this the transformation would be given by these equations, and this would be the derivatives. So if you give an integral like this, it can be pretty easily transformed to this. Okay, so if we are initially we were integrated from x1 this point to x1 e plus a this point, and in y we were integrating from this point y1 e to this point y1 e plus b. Now we have to transform it to from 0 to a and 0 to b, and dx dy can be directly become dx bar by and dy bar. So we the thing to be the thing that should be noted is that we don't know these. We don't know, but we know these, right? So that's why we did this transformation, right? Because we calculate the psi I and psi j's for this particular type of coordinate system. That's why we did this transformation. Okay, so again, we'll be having complicated integral expressions for which we use certain identities. And again, the expression for the Stifford metric would get quite complicated. So it's we wouldn't waste time for that. So again, the thing of interesting here again is the force vector. So again, if we have a some rectangular element and equal force F is acting at each point. Again, consider these arrows perpendicular to the plane. So if we have given force F here, so the total force would be F times area of the rectangle, right? And so this whole total force would be equally distributed by each node, right? So again, again that is intuitive and kind of confirms things for us, kind of verification. So yeah, this was it regarding getting the element level equation and the our element level vectors and matrices for the triangular three-noded elements and four-noded rectangular elements. So now the next thing we are left with is the boundary integral term. So if you remember, uh, so when we break down our weak form and write it in terms of interpolation function, we get a matrix term here is k, but times our unknown variable, and the right hand side we have some body force term we may or may not have, and we may or may not have a boundary integral term. So when we do integration by parts, we get a boundary integral term. So so for suppose if we talk about a triangular element, we'll have to solve this boundary integral on each of the three edges of the triangle, 1, 2, 2, 3, and 3, 1. So we can simply divide this integral into these three parts, right? So likewise, depending on the nature of the element, this can be done. And one thing to note is that just like in the case of 1D FEM, you remember that if we calculate this this q vector uh, at node 2, so the contribution coming from element 1 and element 2 at for this q2, they would cancel out, right? So ultimately, whatever q vector we should get, we get some value for q1, and at 2 we'll get 0. Again 3, for 3 also same, it will be 0, and 4 also be 0, and q5 can be some value. It may or may not be 0, because the points at uh, on the boundary of the domain can have some force applied that doesn't cancel out. You can apply a force easily. So unless a force is specifically given on some node, but unless some force is given, the contribution of for the q vector for that node would be 0 on the internal nodes. So similarly, for suppose we have a system of these elements e1, e2, e3, e4. So if we to get Q contribution here, it's external to the, it means it is on the boundary of the domain. We can have some force. But at this point, contribution from here and here, this would cancel out each other. Here also it would cancel out. Okay. So at the internal faces, the contribution for Q would cancel out. You don't need to calculate that. So now the question is, how do we calculate these boundary integral terms, right? So turns out that for any element, whatever the part of that the element on that boundary is just a 1D. For the case of 2D domain, the part of the element on the boundary of the domain is just a line, simple line. So we just need to solve the integral on that one line straight away. That's all. So consider this triangular element here. We can see how we can transform, we can find the approximation function for that one line element we want. So we can choose any line, 1, 2, 2, 3, or 3, 1, any one. So we just want to transform the our given coordinate system to the specific this coordinate system corresponding to the line. So the thing of importance is this: the dimension, this one dimension of this line, that is S. We, for convenience, we can consider T also here, but we won't need it. You'll see later. So we can write our transformation equation like this, and by substituting the points, we'll get some function. But since we are considering the integral on this line only, so suppose considering on this line 1, 2 here. So we just at this line, t equals to 0 here, right? So we don't need these terms here. We can ignore these, and we'll be left with our main transformation functions. So if you remember, we had already derived the approximation function for the triangular element, where alpha I, beta I, gamma I, these are known constant in terms of the coordinates of the triangle. And if you do this transformation here, you'll get simple approximation function psi 1, psi 2, and psi 3 would be 0, since you are dealing with this line here, right? So here there's no node 3, so psi 3 would automatically go to 0. And if you remember, these psi 1, psi 2, these are nothing but the approximation function that we derived for 1D elements, 1D elements in the natural coordinate system. And that's what exactly we are doing here. It's just a shift from 2D coordinate system to the 1D coordinate system. Okay. So likewise, if we can just do that same transformation, here we had this triangle here. We had a triangle, this triangle here. Likewise, we can do the same for this triangle at this line. So we can do the same here also. We choose this as our the coordinate s, and we can do the same thing, and we can get right now we'll have psi1 equals 0. So psi2 now becomes the first node of this element, and psi3 becomes the second node. And again, similarly, we do the same transformation here on this line, 1, 3, 1. We do this. Now, 3 becomes our node 1 for the line element, and 1 becomes the second node of our line element. Psi 2 is, of course, 0. So, we are just doing this transformation for any line of the triangular element. So depending on which line comes on the uh, outer boundary, we'll do that. Okay, so that's all for this week's content. If there are any doubts, you're welcome to discuss now. We'll try to answer it. Excuse me for a minute. Yes, so you can ask any doubt if you have.
Sir, basically in the final exam, how many questions will come, sir? That any pattern they will send or
Regarding final examination, I'm not much aware. You may need to ask people who handle the course. They might be knowing better. Or you can put this question in discussion forum. There might be other students who might have given any previous NPTEL exam. They might be having an idea.
we are practicing problems. At present, we do not have any doubt. Uh,
Yes, yes, sir. You're not audible. Please, can you repeat?
no, we are doing extra assignment. The assignment problem also we are revising. Also, some assignment problem also will come same
Yeah,
type.
I think
Uh,
so. Yeah, it would be relevant only. Nothing
oh
very
yes.
different. Assignment
Okay.
problems, I think, are essential to practice.
Similar, we can expect.
Yes, yes, sir.
Okay. Okay.
So, does anyone else have any doubt? Please let me know. Otherwise, we can move on to the problem solving session. Okay, so if you're not getting any doubt, then we can move forward.
Yes, sir. Yes, sir. Yes.
Okay. Okay, so since we have been dealing with 2D 2D problems, and we have seen gradient and divergence terms coming up there, so we'll try to uh, take a look at that also. So we need to find the gradient of this function u here, and again the divergence of the gradient of this function u. First part we have u equals to 4x square plus, sorry, 4x square y square. Okay, so can someone answer this? How do we find the gradient? Firstly, what does this operator means? Would someone like to try?
Gradient, sir. Gradient.
Yeah, so gradient actually, what does this mean in terms of vector components? How can we write it? What are its ith component and jth component?
Dou by dou x, dou by dou y.
Right, dou by dou x I cap plus dou by dou y j cap. Thank you. So we can do the same expansion. So 4x square y square. So what we get, we have dou by dou x of 4x square y square I cap plus dou 4x square y square by dou y cap. So derivative with respect to x is 8x y square I cap plus, what is the derivative with respect to y is again 8x square y. Right? I hope I'm doing correct. Now we need to find the divergence of the gradient. Again, the operator still means the same. This time we have a dot product. So how do we do the dot product? We multiply the components of I together and j together. So again, taking the derivative of first term with respect to x, we get 8y square. For second term, we get 8x square. We could this direct expression also. This actually means Laplace operator. So we can simply write dou square u by dou x square plus dou square u by dou y square. Okay. So for second part again, we have dou by dou x of x cube y I cap plus dou by dou x of x cube y j cap. Oh, sorry, it's not dou by dou x, dou by dou y. Fine. So derivative with respect to x is 3x square y I cap plus the derivative with respect to y is x cube. Take it. And again, if we want to find the Laplace, we'll do this directly this time. Dou square x cube y by dou x square plus dou square x cube y by dou y square. So for first term, taking derivative with respect to x 2 times, we'll have 3 times 2, 6 x y, right? And other terms, derivative with respect to y 2 times will make this 0. So we'll be left with 6xy. Okay. So this was just a basic learning exercise. I hope there's no doubt here. If there is, please let me know.
No doubt, sir.
Okay, thank you. So we can move to the next problem. Okay, so we are given a 2D domain here. It's a rectangular domain. How do we discretize the domain to triangular elements or quadrilateral elements? So we have to first discretize this into four triangular elements, right? And we also have to write the element connectivity for each element. Okay, so we first do with triangular elements. So we need four triangles, right? Okay, just connect the using the diagonals. We have element 1, element 2, element 3. Just give the usual numbering to the nodes. Then what do we get? For connectivity for element 1 would be, sorry, we have one extra node. So 5. Yeah, so can someone tell me what would be the connectivity for a node for element 1? So we usually go anti-clockwise. If you remember, we might have discussed this element connectivity in first week, maybe first or second week. Anyone would like to guess?
First element 1 5 and 4 5, sir,
One.
because that is common.
Yeah. So we connectivity means we give the sequence of the node numbers. So it's a triangular element. So we have three node sequence. So we have 1, 5, and 4. It's kind of a matrix that we are forming right now. Likewise for element 2, what will we have? We again have some sequence 1, 2, 5. Can be any. It's not a fixed thing, but we try to form this matrix in order where you'll know when we understand this when we'll study about doing this global to local to global transform, this assembly of the element level equations. So again for element 3 we have, can have 5, 2, 3. Okay. And for element 4, what we have? Can someone try?
534.
Yeah, 534 is fine. Again, it doesn't. It's not a very fixed thing. It can you can change it depending on how you want to sequence this numbering. Okay, so next thing is if you want to divide into quadrilateral elements.
Sir, if local node is there in inside the element, it will goes along. Na? If local code number is given inside of the node,
Local node number
yeah, local
in
node number inside for each
inside.
node, one, two, three. Like if it is given, we will go along that side, na?
Yes, yes, yes. If you're saying, you means to say that suppose we take this element one here. So 154 is the global coordinate number, but when we're dealing with the natural coordinate system, we give this local node number 1, 2, 3. So this sequence actually is this sequence, right? So I wrote this 154 here is because I would be considering the local node number like this. That's why. If I want to consider this local node number like this, 1, 2, 3, then my element 1 connectivity would look like this. 1, 4, 5. So yes, you're right. This actually reflects how we are giving the local coordinate number, local node number. Okay, yes. Is it
Okay,
clear?
sir. Okay, sir. Okay, sir.
Okay. So again, we have to divide into quadrilateral element. So we can do it here. We have this node 1, 2, 3, 4 like usual. We have to make simple quadrilateral. We can make simple rectangles here. Again, we have node 5 here. Sorry, node 5 is here. We have more nodes coming now. 6, 7, 8, 9. Element 1, element 2, element 3, element 4. So how do we write the connectivity for element 1? So I'll write the local node number. So based on that can you guys answer? I'll use a different pen. So inside element 1, the box of element 1, whatever the node numbers written in the blue color are the local node numbers. Okay, so can anyone answer? How do we write the connectivity for element 1?
1, 2, 3, 4, sir.
That's local node number, but in
Yes.
terms of global nodes,
1, 6, 5, 9.
yes, yes. Nice, very good. For element 2, would someone else like to try?
6, 2, 7, 5.
6, 2, 7, 5. Okay, and for element 3,
7, 5, 8, 3.
yes, 7, 5, 8, 3. Again, for element 4,
8, 5, 9, 4.
okay, correct. Thank you so much. So, I hope this concept is clear. If anyone is having any doubt in this, please let me know. We can discuss it now. Okay, so I hope this was clear for everyone. We can move on to the next problem. Okay, so you have to find the interpolation function for the quadrilateral which is connected by the following points. So we can draw the quadrilateral here. We have our first node as 0, 0. Then we have our second node as 5, 0. And then we have our node 3 at 5, 3. And then we have our fourth node as 0, 3. Just comment things. So we have this rectangle element and we need to find the interpolation functions. So I have one. How many interpolation function do we have here?
4.
So yeah, thanks. Psi 1, psi 2, psi 3, psi 4. That is what we need to find, right? So what is the procedure to this? So first of all, we write the approximation for this such type of element. So since we have four nodes, so our approximation function would naturally have how many unknowns? So we'll write a polynomial with how many unknown terms? Anyone?
4, sir.
Yeah, thanks. So we have our approximation function in this form. Also, if we write our approximation function in terms of nodal coordinates, we know that we write this as I equals to 1 to 4 uj psi j, right? Which can be written as u1 psi 1 plus u2 psi 2 plus u3 psi 3 plus u4 psi 4. Okay, so to get the equation, we substitute these values for each node points. So at node 1, so using this is equation 1 and this is equation 2. So using equation 1, we can straight away get substitute the value of x and y. So x is also 0, y is also 0. So what should be the value here for ue? Should be equal to c1. Okay, and using equation 2, what should be the value of ue? Someone please answer.
U1 is equal to C1.
Yeah, right. So our elemental the value of our solution for this element would be u1 using equation 2 for node 1, right? Again at node 2 using equation 1, what do we get? c1 plus
U2 is
u2.
equal to
Yeah, so that I'll write on right hand side. So using first using equation 1, we'll get c1 plus 5c2 since y is 0, right? And using equation 2, we get u2 because all the other sides become 0 at node 2. Psi 1, psi 3, psi 4 becomes 0 and psi 2 becomes 1. We'll get u2. Again at node 3. Now we have x equals to 5 and y equals to 3. So using equation 1 we have u1 plus uh, x is 0, though we'll have 3c3. No, sorry, x is not equal to 0. My bad. We have 5c2, then we have 3c3, and we have 15c4. And that is equals to, using equation 2, what do we get? The value of u is 3, right? So now at node 4, uh, using equation 1, at node 4 x equals 0, so we have only two terms, c1 and c3y. c3y is 3c3, and this again is equals to u4, right? Using equation 2. So we have four unknowns here, c1, c2, c3, c4, that we'll have to solve here. So it is, if we'll try solve it manually, we get c1 equals to u1. So this we immediately got from at node 1. Now we substitute this value in node 2, in equation for node 2, we'll get the value of a c2, which is equals to u2 minus u1 divided by 5. And similarly for, if we substitute in the value for node 4, the equation for node 4, we'll get the value of c3 also, to nothing but u4 minus u1 divided by 3. So now we substitute all these values in equation, in the equation corresponding to node 3. What do we get? We need to find, we left with the c4, right? Okay, so we have substitute each value. c1 is u1, and 5c2 is nothing but u2 minus u1, plus c 3 times c3 is u4 minus u1, plus 15 c4 is u3. Okay, so what do we get here? c4 equals to, I hope I'm doing right, please guide me if there's an issue. c4 is equals to u3 minus u1 minus of u2 minus u1 minus of u4 minus u1, so all divided by 50. So I hope we got all four constants, and now we substitute this back into equation 1. So we have c1 equals to u1 plus c2x, c2 is u2 minus u1, plus c3 is u4 minus u1, by 3, sorry, y, plus c4 is a big chunky expression, u3 minus u1 u2 minus u1 plus u4 minus u1 upon 15xy. So now we try to so this all is equals to u. So now we try to arrange this so in the form of equation 2. So we put together all the terms for u1. For u1 we have first term, second term we have minus x by 5, third term we have minus y by 3, and do we have anything else? Yeah, we have okay, so we have minus u1 15 plus u1 and we have minus y by sorry xy by 15. Yeah, is there any doubt for with anyone?
So plus xy by 15.
Plus yeah, I'm so sorry. Yeah, thank you. Then again for u2 what do we have? We have uh, x by 5 here, and we have do we have anything in second term? No, we have something in third last term. So we have minus 6y by 15, isn't it?
Yes, sir.
Fine. Then for u3 what do we have? We don't have anything in first term, nothing in second, third. We have something in the uh, last term. So we only have one u3 term, that is xy by 50, right?
Yes, sir.
So for u4, do we have anything? First term, no. Second term, no. Third term, we have y by 3. And for fourth term, we have yeah, minus xy by 50. Okay, so comparing it with our equation 2, which is u1 psi 1 plus u2 psi 2 plus u3 psi 3 plus u4 psi 4. So these are expressions. So we have done the same thing in the class, that right? For there we had some unknowns a and b there in terms of the sides of rectangle. Now I use some actual values just to demonstrate how this derivation was done. So there also we had derived a direct formula in the end, that it would be for psi 1 would be equals to 1 minus x by a times 1 minus y by b. So if we have a equals to 5 x by 5 and b equals to 3, we'll get the same thing, 1 minus x by 5 minus y by 3 plus xy by 50. And likewise for others also, side 2 also we derived as x by a times 1 minus y by b. We'll get the same thing. Likewise for side 3, side 4, same thing. Okay, so there's nothing new in this problem. It's the same thing that we studied in the lecture. Just a demonstration for that. I hope this was clear for everyone. If there's any doubt, please let me know.
No doubt, sir.
Okay, okay. For I'll wait if there is any doubt for anyone else. Meanwhile, I'll just write this. Okay, so if there are no doubts for anyone, we can move forward. Okay, so we'll have to do the same thing again for just revision for the triangular element. So we have our first node at 0, 0, and we have a second node at 1, 0, and then we have third node at 1, 1. So this is our triangular element. Again, for triangular element, we have three nodes. So what should the interpolation function look like? How many unknowns? Three unknowns, right? And using the nodal values should be equal to u1 plus psi1 plus u2 plus psi2 plus u3 plus psi3. This becomes the second equation. So again we follow the same procedure. We substitute the values of equation 1 and 2 at each node. We have node 1 here. So using equation 1, what is the value of our function u becomes? In equation 1, we have x equals 0, y equals 0, so we just get c1. And using equation 2, we are left with u1. At node 2, what are we left with? So now x equals to 1 and y equals to 0. So we are left with c1 plus c2 and by 0. And using equation 2, we have at node 2 side 2 equals to 1 and other side are 0. So we get u2. Again at node 3 in the equation 1. At node 3 we have x equals to 1, y equals to 1. So we get all three constants c1 plus c2 plus c3, and which is equals to using equation 2 we get u3. So these are our three equations for to calculate the three unknowns c1, c2, c3. So we could have done using by making the matrix for the system of equation, and then we'll have to find the inverse. It will be time consuming. So we'll get this matrix here. 1 0 0 1 1 0 1. We have C1 C2 C3, which is equals to U1 U2 U3. We need to are unknown in this vector here, so we need to transfer this matrix from here to here, take the inverse. Otherwise we can do it simply by this simple manipulation. We know that C1 equals to U1. We substitute this in equation 2 here, so we get C2 equals to U2 minus U1, and we substitute these two value again here in third equation. We get C3 equals to U3 minus U1 minus U2. Okay, sorry, not minus U2. So C2 is equals to U2 minus U1. So we'll get U2 minus U1, and this would actually cancel out U1. So we get U3 minus U2. Right. Okay. Please confirm if I'm doing right. Let me know if there's some mistake here. U3 minus U2. Okay, fine. So we got our three unknowns here. So we can again substitute it. So we need to substitute these. So what do we get? So we have C1 equals to U1 plus C2 equals to U2 minus U1 times X, right? Yeah. Then C3 equals to U3 minus U2 times Y. So now we try to uh, rearrange the terms in form of equation 2. So we take the coefficient of u1 together. We get 1 here, get minus x, get minus 5. So no, not minus 5. Don't have u1 anywhere else. So we have u1 first term, we get 1. You have u1 in second term, we get minus 6. We don't have u1 anywhere else, right? For u2, we have u2. No, there's no u2 in first term. We have u2 in second term, we get x. We have u2 in third term, we get minus y. Okay, and then for u3, we don't have u3 in first term, we don't have in second term, we have u3 in third term, which is y. Alright, so if we look at equation, we write the equation 2. We have ue equals to u1 psi 1 plus u2 psi 2 plus u3 psi 3. Comparing the two, we get psi 1 equals to 1 minus x, psi 2 equals to x minus y, and psi 3 equals to y. Okay, so these are the interpolation functions for this type of element, linear interpolation function. We can just verify if we got the right answer by checking if we are getting the value of psi 1 at node 1. What do we get? At node 1, both x and y are 0. So we get 1, which is right. We get psi 1 at node 2. So we have node 2, we have x equals to 1, y equals 0. We get 1 minus 1 equals to 0. And this is correct. Psi 1 at node 3. Again 1 minus 1. Yes? Any doubt? You're muted. If you want to ask any doubt, you can unmute yourself. So checking for side 2. At node 1, we have both x equals 0, y equals 0. We get symbol 0. That's right. At node 2, we have x equals to 1, y equals 0. We get value 1. This is also right. Side 2 at node 3, we have x equals to 1 and y also equals to 1. So 1 minus 1, you get 0. Again, for side 3 at node 1, we have x and y both 0. We get 0 value. Side 3 at node 2, we have x equals to 1, y equals 0. Again, we get 0. Side 3 at node 3, we have x equals to 1 and y equals to 1. So we get a value 1, right? So if you can check that the value of the uh, interpolation function for the corresponding nodes is equals to 1. We're getting it, and for other nodes we're getting 0, right? So this is kind of a verification if we're getting the right interpolation functions. So I hope this problem was also clear. If there's any doubt, please let me know. Okay, so if there's no doubt, we can move forward. Okay, so we studied some basic identities for integration. We can practice them now. So, so we have to find these two integrals. So first integral is xy dx dy, and we are given a triangle this. We are given triangle 3 nodes at 0 0 2 2 4 4. Sorry, 4 0. Oh, my bad. This is wrong name. Sorry. So yeah, this is 4 0 and this is 2 2. Yeah, so we're giving this triangle here. We need to find the integral over this triangle, basically. So what should be the identity for first part here? It is nothing but I11. Does anyone remember the formula for I11? So it is the general form meanwhile. Anyone?
xy integral xy dx dy.
Integral x. Yeah, yeah, right. But I'm asking the formula for this, the value for this, the solution for integral actually.
Zero, sir.
Is it zero? Not sure. I'll have to check the formula. Where did it go? Yeah. So we have 1 1. Yeah. Here. This is 1 1. A by 12 is equals to A by 12 summation of xi plus 9 times x cap y cap. Okay. Right. I hope so. So, if we want to find this term, we first need to find the area of the triangle A. So, area is equals to half base into height, right? So, looking at the coordinates, what should be the value of base here? Anyone? Base is equals to 4, right? And what should be the height? So, it's the the line horizontal line here is on the y equals to 0 axis, x axis. So the y coordinate of third node is the height, right? 2. So we get area equals to 4. 4 by 12 here. Now we have to do the summation xi yi. So for first node we have 0 into 0. Say for second node we have 4 into 0. For third node we have 2 into 2. Correct? And plus 9 times. What is the value of x cap? I think it's sum of all the x coordinates, right? X cap is, yeah, sum of all x coordinates. So that's 0 plus 4 plus 2. Then what's y cap? Sum of all y coordinates. That's 0 plus 0 plus 2. So we are left with 1 by 3. 4 plus 4 plus 2 6 into 2 12. So 72, right? So we get 76 by 3. Okay, fine. I hope this is right. Please, someone please check and verify if I'm doing it right. So you can even check this solution. So this integral is this integral in this triangular region can be integrated as x equals to 0 to x equals to 4, I guess, and y equals to 0 to y equals to 2. I hope, should it be? Let me just check on my calculator. This is the answer for this. I'm not sure that this is how we'll do this integration over this triangle.
16, sir.
This is giving you 16. Then this must be some issue. So this actually does not mean that. Okay, so we need to solve this. Okay, so this should be the value for I11. Now the next part is, yes, yeah, I remember now. So we used to draw some strip for this kind of integration. So uh, suppose if we draw some strip like this, so we need to know the equation of this this line here and this line also. So yeah, so the integral limits would be a function that is the equation of this line. So that's a rather complicated thing, and this is a very straightforward formula to do this. So now you can, even I can appreciate this use of this formula. So we are given this integral, it's nothing but I02. So does anyone remember the formula for I02? I remember this part A by 12. Would anyone like to fill in here? Okay, let's see the formula. Okay, summation of y square and 9y cap square y square. So this means we have area, we know 4 by 12, it's the same triangle. Then we have to take the square, sum of the squares of y coordinate. So we have 0 square plus 0 square plus 2 square. Then we have to take the square of the sum of coordinates, plus 0 plus 2. So we get 1 by 3 times 4 plus 9 times 4, 36. Okay, so we have 40 by 3. So that should be the value of this integral. Okay, so this was really quick using this formula. If we use the normal conventional method to solve this area integral, it would be time consuming. So I hope this was clear. There's no way to do this area integral on calculator. Otherwise, I would have confirmed these answers. Okay, if there's any doubt, please let me know. Otherwise, we can move forward. Okay, so for the triangular elements in problem 4, calculate the force vector. So, problem 4 we have this triangular element. Okay, again, first of all, we need to write the equation for the force vector. Can someone tell me what is this integral here? So we have some distributed load F times the shape functions and of course dx dy. So we have this triangular element here. So node 1, node 2, node 3. Okay, so we have this integral. Okay, so first of all, what are psi i's here? We did calculate it. Psi 1 was 1 minus x, right? Psi 2 was x minus y. And then even remember psi 3?
Why?
Yeah, nice, thank you. Just let me confirm once. 1 minus x, x minus y, and y. Right? That's what we derived. Okay, so now we have defined F1 first. So we have this area of this over this triangle. So right now we don't know the F. This F here. It's not given the problem. We can assume some constant value. We can just assume it equals to 1. So we have psi 1 times dx dy. So we have this triangle times 1 minus x times dx dy. Right? Okay, so again we'll try to use the knowledge we have. We have this integral dx dy minus this integral x dx dy, and this is nothing but I00, and this is nothing but I10. So now we need the formulas. Anyone please help me? Someone help me. F1 is, so what was the formula for I00?
area of the triangle, that is 1 by 2.
Yes, thank you so much. So area of the triangle is, we have simple given base of 1 and height of 1. So it's 1 by 2. Thank you, sir. Sorry, it's only I00. We still need I11. So I10. I10 would be, anyone would like to guess?
1 by 2 times of x1 plus x2 plus x3.
Okay, you mean area of triangle times summation of x, x coordinates basically, isn't it? Let me confirm once. Hope we're doing right. Yeah, thank you so much. We have half minus half of x1 is 0, x2 is 1, and x3 is also 1, right? So we have half minus, it becomes 1. We have minus half. Okay, so this is right. Okay, anyway. So f2 is this integral side to dx dy. So we have x minus y times dx dy. It makes it equal to I10 minus I01. So we know the formula for I10, that is A times summation for xi. And what is formula for I01?
A times summation yi. Okay.
Yeah, thank you. So we have half of summation of x is 0 plus 1 plus 1. Then we have half of summation of yi is 0, 0 and 1. So we have half into 2 is 1 minus half. Get half. Okay, like we are out of space. Okay. Try to do F3 here. Whatever space we have. So F3 is psi 3 is y dx dy. So this is nothing but I01, for which we just wrote the formula as a area times summation of y. 0 plus 0 plus 1. So we get value of half. Okay. So shall we move forward? Okay, so we are given this problem here. So this is going to be lengthy problem. You have to do all the things here. So we have this Poisson's equation here. So first thing we need to do is we need to write the weak form of the equation. And if we do that, I'll just try to simplify the equation. So it's constant. Let's write it like this. So if we write the weighted residual statement, I'll just write it quickly. If there's any doubt, please let me know. So we have dou w by dou x, dou u by dou x. That's 5 times dou w by dou y plus dou u by, sorry, not plus, times dou u by dou y. And then we have this stuff. Plus apart from that, we'll have some boundary term that I'll just write quickly here. W times dou u by dou x plus w, sorry, w is already multiplied, dou u by dou y and y. That's integrated over boundary. So for what is of our interest is the for the stiffness matrix and force vector. So if we approximate u as uj psi j, w as psi I, can write the above equation as dou psi I by dou x dou psi I by dou y times dou psi j uj times dou y. And here we can, so I'll just transfer this 5 here, right, 5 here, thus we have this boundary term. So if we rearrange this as times uj, then we have this term, sorry, w is now psi. So can someone tell me what term corresponding to our stiffness matrix and which term corresponding to our force vector? we can write this equation like this: k, which is a matrix, times a vector u, we get a vector f plus vector q. This is how we generally write our algebraic equation in FEM. So this here is our k, u, this is the q is a boundary term, right? So we need to find these two. First of all, we need to get our psi and psi j. So we're given a triangular, a triangle here. One zero zero 1 0 0 1 1 0 0 1. So not 3. So again, if we'll try to get the shape function for this triangle, it'll take some time. Can do it directly. We can write this as c1 plus c2x plus c3y equals to u1 psi 1 plus u2 psi 2 u3 psi 3. So for node 1 we get c1 equals to u1, then we get for node 2 we get c1 plus c2 equals to u2, and for node 3 we get c1 plus c3 equals to u3. We solve, we get c1 equals to u1, we get c2 equals to u2 minus u1, we get c3 equals to u3 minus u1, and this will give us u equals to u1 plus u2 minus u1x plus u3 minus u1 y. So we have u1 1 minus x minus y plus u2 times x plus u3 times y. So this gives us our approximation function psi1 equals to 1 minus x minus y, psi2 equals to x, psi3 equals to y. So we'll first start with finding the force vector. That will take lesser time. Equals to, so we have to integrate this over this triangle area, for which, so we'll just take 1 by 5 out, calculate that later. Psi I dx dy. So sorry, so we have f1 equals to 1 by 5 1 minus x minus y dx dy. So we get I00 minus I10 minus I01, right? So we have already written the formula for I00, that's the area, which is again for this triangle area equals to half. Then we have area times, so let's simply write it. We have area minus area times the summation of the x values. So x value 0, 1 and 0. So that's 1. Again we have I01 is area times summation of y values. So y values are 0, 0, 0 and then 1. So minus. So this half of cancel, we have 1 by 10. Alright, so for F2 we have 1 by 5 times x dx dy, which is 1 by 5 times I10. And I10 we already calculated is equals to half, 1 by 10. 3 equals to again 1 by 5 times area y dx dy equals to 1 by 5 times I01. I01 is again we have it as half, 1 by 10. Okay, so this is with our force vector. Now we'll try to get our K matrix. So first of all, what is our dou psi 1 by dou x?
Sir, what about F1, sir? Can force vector be negative value, sir?
Yeah, it can.
So then F1
Sorry,
is
sorry.
minus 1 by 10.
Yeah, it should be minus 1 by 10. Thank you. So dou psi 2 by dou x is 1 and dou psi 3 by dou x is 0. Dou psi 1 by dou y is minus 1. Dou psi 2 by dou y is 0. Dou psi 3 by dou y is 1. Okay, so we'll try to do as many components of this K matrix as possible. So first of all, K11. So we have of dou psi 1 by dou x, dou psi 1 by dou x plus dou psi 1 by dou y, dou psi 1 by dou y. So dou psi 1 by dou x is minus 1, again minus 1 times minus 1 is plus 1, and dou psi 1 by dou y is again minus 1. So we have 1 plus 1, we get 2, 2 dx dy. So again 2 times I00, and I00 is the area, 2 times half, get gives us 1. Alright, then we have K12 psi 1 by dou x, dou psi 2 by dou x plus dou psi 1 by dou y, dou psi 2 by dou y dx. So we get dou psi 1 by x is minus 1, dou psi 2 by x is 1, so we get minus 1 here, and then dou psi 1 by dou y is minus 1, dou psi 2 by dou y is 0, so we get 0. Second term becomes 0. You have minus 1 times dx dy. So again dx dy is 100, that is half, so we get minus half. So we do is, so next is K13. by dou x dou psi 3 by dou y plus dou psi, sorry, not y, 6 dou psi 1 by dou y plus dou psi 3 by dou y, sorry, not plus, multiply dx dy. So dou psi 1 by dou x is minus 1, dou psi 3 by dou x is 0. So first term is 0. And then dou psi 1 by dou y is minus 1 and dou psi 3 by dou y is 1. We get again minus 1 here. Dx dy, which is same as the previous term, we get minus half. Alright, so this is the time taking thing. Uh, like the same way if we go on, we'll get the other terms of this K matrix also. So it would be a 3 by 3 matrix. Uh, we'll stop here, and if there's any doubt, you can ask now. So you can try solving further terms in this by yourself. It's pretty straightforward now. If sometime we can take up a simpler problem. Okay, we can try this. So we given a three-noded triangle. First node is at 0, 0. Second node is at 3, 0. Third node is here at 1.5, 1.5. So we need to find the interpolation functions at each node at the center of the triangle. So at each node, I think it's pretty straightforward. We don't need to calculate the interpolation function actually. So can someone tell me what should be the value of psi 1 at node 1, 0, 0? You guys can answer this. Value of psi 1 at 3, 0. Value of psi 1 at 1.5, 1.5. Please go ahead and answer this.
100.
Yes, 100. And value of psi 2 at 0, 0 would be again 0. And value of psi 2 at 3, 0 would be 1. Value of psi 2 at 1.5, 1.5 would be 0. For psi 3 at 0, 0, node 1 it would be 0. Psi 3 at node 2 would again be 0. And psi 3 at node 3 should give 1. So that's the basic rule of designing the interpolation functions. That it should give a value 1 at the corresponding node and 0 at all other nodes. And the variation between depends on the choice of the functions. If they're linear functions, the variation is linear. The quadratic, the variation is second degree polynomial. All right. So, but we also need to find the value at the center of the triangle. So for that, we actually need the interpolation functions. So we'll need to find psi 1, psi 2, psi 3. How do we do that? We have the same procedure. 1 plus x plus c. 2y, and which is equal to two side. We'll just quickly do it. Sorry, not 1. My bad. C1 plus C2 plus C3. So we get C1 equals to U1. We get C1 plus 3C2 equals to U2. C1 plus 1.5 C2 plus 1.5 C3 equals to U3. You know C1 equals to U1. From there we get C2. C3 equals to U3 minus Q1 minus 1.5 times C2 is 2 minus Q1 by 3. Okay. So next is we substitute the value back. We get U1 plus U2 minus U1 3x plus U3 minus U2 by 2 minus 2y. So we rearrange 1 minus x by 3 minus 3y by 2 plus u2 times we have x by 3 minus y by 2 plus u3 times we have dy, right? Okay, so this gives us psi 1, psi 2, psi 3. So substitute the value of, so first of all we need to find the value of centroid. So where is centroid? The coordinates of centroid are equals to the average of the coordinates. So x is 0, 3, 1.5. 0 plus 3 plus 1.5 divided by 3, and similar for y, 0, 0, 1.5. So we have 4.5 divided by 3 is 1.5 only, and it's 3 by 2. 1.5 by 3 is 0.5. So value of psi 1 at 1.5, 0.5 is 1 minus 1.5 by 3 minus 3 into 0.5 by 2. This gives us 1 minus half minus 3 by 4. Half minus 3 by 4 is minus 1 by 4, isn't it? Please see, check if this is correct. Side to it 1.5 comma 0.5 is x by 3 minus y by 2. So 1.5 by 3 minus 0 by 2. So that's half minus 1 by 4. That's 1 by 4. And side 3 is side 3 at 1.5 comma 0.5 is this y 0.5 or half. Okay. Okay, so I think we are out of time now. So if there's any doubt, we can discuss it now, or otherwise we can end the session here. Please let me know.
No doubts.
Okay, thank you so much, sir. If there's any further doubt, you can
Thank you.
yeah, you can post the question in the discussion forum. Uh, okay, so thank you so much for attending the session. We would meet next week, Tuesday, 7 p.m. again for discussing the content of the next week, week 7, and we'll discuss the problem related to that. So I thank you all again, and okay, I'll end the meeting now.
Thank you, sir. Thank you, sir.